Welcome to the League of Women Voters, Monterey County monthly meeting. We're delighted to see so many people here. Now I'd like to invite Jim Emery up to introduce our speaker.
Well, it's certainly gratifying to see such a turnout. This is extraordinary. It is very good evidence that the issue of climate change is reaching everybody. It's still, though, a very serious problem to deal with it. There are some very difficult components of the problem. One, the problem is inherently very complex. We'll get sort of a little bit of evidence of that in Mike Clancy's talk. It deals with uncertainty and probabilistic outcomes. That's not easy for many people, as evidenced by their willingness to gamble on weird gambles. It requires long-term waiting for the outcome. Delayed gratification is not one of America's most prominent components in the political area. It has serious opponents. There's big incentives for people with lots of money to cloud the issue, and that has been done. We saw that with tobacco, and it's coming and has been practiced now. It requires inspired, energetic leadership, Churchillian leadership, and I don't think most people would claim that we have that now. So the problem is serious. It's going to be hard to deal with it, but the fact that there's as much interest there as there is now, and people are becoming more and more convinced, I think there is some room for optimism. Mike Clancy is, I think, the perfect guy to talk about it. He has a very solid background. He has a bachelor's degree in oceanography and a master's degree in meteorology. Those are encompass much of the science that we're talking about. So that's an excellent background. He joined the Navy's Fleet Numerical Organization in 1983, was it? And he was selected as the Director of Technology and Scientific Technology in 2005. He has a world of experience. He's been honored in many ways at his government job and in other areas. So I think we're all very fortunate to have such a qualified person talk about such an important topic. Mike?
Thank you, Jim. Thank you, Howard. And thank you most of all, everyone, for coming today, this important topic, and I really appreciate you being here. I'm going to cover a lot of material. I move kind of fast. This is going to be a science-intensive brief, so if things that just aren't making sense to you, you can't tell what you're looking at, please raise your hand and stop, and I'll clarify. So we're going to start by, I'm going to be taking you back, way back, 5 million years. What we're looking at here is the global mean surface temperature of the Earth from the present time back 5 million years. And what you see here is beginning about 2.5 million years ago, the beginning of what's called the Pleistocene epoch, the Earth started going into ice ages. And we've been through many ice age cycles, dozens and dozens of ice ages. The first 1.5 million years of the Pleistocene, we were on a 40,000 year ice age cycle. And then beginning about 1 million years ago, that cycle changed to be about 100,000 year ice age cycle. So why am I talking about ice ages? Why am I showing you this? Well, the human-induced climate change that we're all concerned about occurs against a backdrop of this natural climate variability. And the ice age cycle, in particular the 100,000 year ice age cycle, has dominated climate variability for the past million years. Now, do we understand that? Absolutely, we do understand the ice age cycle. It's no mystery. It's not something which we don't understand. It's in fact driven by orbital variations of the Earth, and in particular, something called eccentricity. It's the variation of the Earth's orbit around the Sun being more circular or more like an ellipse. Obliquity, which is the tilt of the Earth. And the eccentricity cycle occurs on a 100-year period, and it's actually driven by the gravitational force of Jupiter and Saturn on the Earth. The obliquity cycle, 40,000 year cycle, the Earth tilting back and forth, is driven by the gravitational force of the sun and moon acting on the Earth. These are called the Milankovitch cycles after Milutin Milankovic, a Serbian astronomer and geophysicist, discovered this about 100 years ago. And in fact, they drive the ice age cycle. It works like this. When these orbital variations conspire to decrease solar radiation striking the northern hemisphere in the summertime, these feedback loops kick in here, which amplify that, particularly the snow-ice feedback loop, which you might have read about. And the way that works is decreasing sunlight or decreasing global temperatures caused by this reduced solar radiation hitting the Earth yields increasing snow and ice in the northern hemisphere where all the land, most of the land is. And that reflects more sunlight back out to space, which contributes to decreasing global temperatures. You basically go around this feedback loop. And there are other feedback loops here that are important as well. So that's how you get into an ice age cycle. This is how you get out of an ice age cycle. When these orbital variations yield increasing solar radiation striking the Earth, then you basically go around the feedback loops in the other direction, and the Earth warms over about a 10,000 year period, and you come out of the ice age cycle. Now I want to look back here again, and we're going to zoom in way over here and look at the last 22,000 years of the Earth's temperature. And it looks like this. So we're going from the present time back 22,000 years. Here's where human civilization began, just for reference, about 9,000 years ago. This is the last ice age right here. And this warming trend was the recovery from the ice age driven by the eccentricity cycle. So basically what was happening here, the Earth's orbit around the sun was becoming less like an ellipse and more like a circle, and that was yielding warming in the northern hemisphere summer. And that warmed us out of that ice age cycle into what's called the Holocene interglacial period, which we live in right now. And notice that there has been a slow cooling trend over the course of the last 10,000 years or so. That's driven by the obliquity cycle, this tilt of the Earth on its axis. And what's been happening is the Earth has been losing tilt. In fact, over this period, the Earth has lost about a half a degree of tilt, which has contributed to this cooling trend. There are a couple of other identifiable features here. This little bump here is called the medieval warm period, back in the time of knights and castles and so forth. This is called the Little Ice Age. Most famously, the River Thames froze over during this period, time of Elizabethan England. And finally, we have this red spike, which in fact is what we're concerned with. It's the post-industrial global warming that we're so concerned about. Well, when you see it in this context, a couple things come to light. First of all, it's going in the wrong direction. We should be cooling because of this obliquity cycle and because of the Earth losing tilt. You can see the cooling trend here. We should be cooling, but suddenly we've upturned. And we're warming very fast. In fact, we're warming about 20 times faster than natural variability. It takes about 2,000 years to warm 1 degree centigrade, but we've warmed 1 degree centigrade in 100 years. That's 20 times faster than natural variability. So we're warming 20 times faster than natural variability, 20 times faster in the wrong direction. So what does 20 times faster in the wrong direction mean? Well, imagine you're playing golf at Quail Lodge, and you have a golf cart. You take a wrong turn, unfortunately, and you find yourself westbound on Carmel Valley Road. And unfortunately, it's car week. And suddenly you see a Lamborghini coming the other way, 200 miles an hour. You're going along at 10 miles an hour. Here's a Lamborghini going 200 miles an hour the other way, and they can go that fast, by the way. That's the difference here. You know, the natural climate variability is like the golf cart, and what we're seeing the last 100 years is like the Lamborghini. Pretty hard to confuse a golf cart with the Lamborghini. This is not natural climate variability. So what's going on here? Well, let's zoom in some more. Now we're going to look back about 150 years. And what we're looking at here, again, is global mean surface temperature of the Earth. It's the surface temperature of the Earth averaged over the entire face of the Earth. 5 different sources, and this is the Japanese product, the Japanese Meteorological Agency, the Europeans, the UK Met Office, 2 American products, a NASA temperature analysis and a NOAA temperature analysis. And the point here is these 5 different independent analyses based on different techniques, different groups, different analysis techniques, and so forth, all paint the very same picture. And the picture is as follows. Not much happening from 1850 to 1880, a slight decline 1880 to 1910. Beginning in 1910, though, we see this upward movement. Slight decline from 45 to 75, but beginning in 75 and continuing to the present time, a dramatic upward movement of the temperature, such that we are now a little more than 1 degree C above the pre-industrial level. Notice all the zigs and zags here. It's kind of like the stock market. That's like volatility in the stock market. It doesn't go up in a straight line. There are these zigs and zags. Remember that. We're going to talk about those a little bit later. So I'm going to actually show you an animation of one of these products. It's going to be the NASA surface temperature product. And it's going to run from 1880 up to, I think, 2017. A couple of things about it. What's going to be depicted here is temperature anomaly. Temperature anomaly is just a fancy way of saying temperature difference. Temperature difference between the 1951 to 1980 average. And here's the scale here. So where it's white, there's no difference between the 1951 to 1980 average. Where it's yellow or orange, it's warmer. Where it's blue, it's cooler. So the more you get towards orange, the more it's warm. The more you get towards blue, the more it's cool. So we're going to take a look at that animation. And one final subtlety, there's a running 5-year window applied to smooth it out, so to kind of smooth out all those zigs and zags and focus more on the long-term trends. I'm going to call out the decades, so you don't have to worry about that part. And pay particular attention in what happens when we hit the 1970s. You remember from this chart right here, there was this rapid upward movement beginning about the mid-70s. And you'll see that in this animation. So here we go. So this is the 1900s, 1910s, 1920s, 30s, 1940s, 1950s, 1960s. Now watch what happens in the 70s, 1970s. And that takes us up to 2018. So pretty dramatic, but also it shows a couple of things that are worth remembering. First of all, the land is warming faster than the sea. You can see that the land is orange here, the sea is yellow, but the sea is warming. And the ocean is definitely warming. Turns out about 95% of the heat from global warming is actually going into the ocean, but the ocean is warming slower than the land because the ocean has much higher heat capacity. It can absorb a lot more heat without warming up very much. So the land is warming faster than the ocean. The higher you go in latitude, it's warming more. So the Arctic is warming more than the lower latitudes. And that's not a good thing because that's where the ice is. And that's, of course, the melting ice contributes to sea level rise. Note that the western United States is warming substantially more than the rest of the United States. About the western one-third is warming quite a bit more. We'll talk about that later in terms of local impacts. Note that it's not warming everywhere. It's not warming everywhere. There are some areas that are cooling. For example, this region right here. This has to do with changes in the Gulf Stream ocean circulation. But there are other areas where it's cooling or there's very little change. Global warming is a global phenomenon. You know, you can pick a spot where maybe it's not warming. You really need to look at the global aspect of the problem. So the question is, do we understand this, or is this just a big mystery? And the answer is absolutely we understand this. In fact, we've understood it for years. The science is settled, and it's actually pretty straightforward. The best way to think about it is in the context of the Earth's global energy balance, and what we're looking at here is an annually averaged, globally averaged flow of energy on the Earth. And these are flows of energy in terms of watts per square meter. And it's actually pretty straightforward. You know, it's not quantum theory, it's not relativity, it's pretty straightforward. It's the greenhouse effect. It's been known about for over a century, and essentially works like this. The incoming solar radiation warms the Earth, and the Earth is cooled by reflected solar radiation. Some of that reflected solar radiation is reflected by clouds and aerosols in the atmosphere, such as dust and pollution and volcanic ash. Some is reflected from the surface, particularly from ice and snow-covered areas. And then it's also cooled by outgoing infrared radiation or long-wave radiation. And that outgoing long-wave radiation is impeded by greenhouse gases in the atmosphere. It's like a blanket. Like you go to sleep at night, you have a blanket, it holds the heat in. And that's what these greenhouse gases are doing. And the problem is human activities are increasing the greenhouse gases. It's like you're sleeping at night, you're comfortable, but somebody keeps piling more blankets on, blanket after blanket. Pretty soon you're going to get too warm. That's what's happening. Human activities are loading up the atmosphere with greenhouse gases, and that's trapping the infrared radiation. In fact, you can see right here, 396 watts per square meter of infrared radiation goes up to try to cool the Earth, but 333 end up coming back down because of being trapped mainly by the greenhouse gases. By the way, it's good we have some trapping going on here. If we could suddenly wave a magic wand and, for example, eliminate the greenhouse properties of water vapor, get rid of all these greenhouse gases, the Earth would cool dramatically. We would go into a permanent ice age, and Monterey would be under an ice sheet hundreds of meters thick. That's what would happen if we didn't have the greenhouse effect. The problem is And that's what, we're just putting on too many blankets. We're just, it's getting thicker and thicker, and it's warming too much. Now, this is not just me talking. This is the overwhelming international scientific consensus as reflected on this partial list of leading science organizations who have confirmed human-induced global warming. This has been understood and settled for years. The science is absolutely settled. Unfortunately, the politics, of course, are not, but the science absolutely is settled, as illustrated by this overwhelming international scientific concurrence. So let's talk a little bit about the greenhouse gases. The main greenhouse gases of concern are carbon dioxide, methane, which is also known as natural gas, nitrous oxide, and fluorinated gases. Now this is a snapshot in time of the impact of these greenhouse gases. Carbon dioxide has the major impact. 72% of the current global warming is being caused by carbon dioxide, and it goes on down here. That's mainly because there's so much carbon dioxide in the atmosphere. It isn't the most powerful greenhouse gas. In fact, as you go down the list here, the potency of the greenhouse gases actually go up. It's just that there's so much carbon dioxide in the atmosphere that it is the dominant contributor to the rate of global warming. So let's talk a little bit about CO2, carbon dioxide. CO2 levels are usually reported in terms of parts per million, and the pre-industrial level was about 280 parts per million, and now it's over 413. That's an increase of almost 60% over the pre-industrial level. You can see it really started going up dramatically here. The total mass of CO2 in the atmosphere is also of interest, and it turns out from 1850 to 2018, we've emitted about 2 trillion tons, 2 trillion, not million, 2 trillion tons of CO2 in the atmosphere, and about 1.1 trillion tons are still there. So what that kind of tells you is we're putting CO2 in the atmosphere about twice as fast as natural processes can take them out. And we are currently emitting CO2 in the atmosphere at the rate of about 40 billion tons per year. 40 billion tons, it's really quite a lot. So this is where we are now, seen in the context of the ice age cycle. The question is, where are we going? Well, that depends on what we do, where we are the citizens of the world. If we follow the recommendations of the Paris Climate Accord, which was basically to achieve carbon neutrality by 2050. Carbon neutrality means the amount of CO2 we're putting in the atmosphere equals the amount that's being taken out by natural processes, such that CO2 ends up leveling off by 2050. That would require reducing CO2 emissions globally by a factor of about 2, which is a heavy lift. That would be very difficult to do, but that's the goal. This is where we'll end up if we do that. And but if we don't do that, for example, if we withdraw from the Paris Accord, like the United States has done, if other countries in the world follow our lead and basically throw up their hands and say, we don't believe this, we're not going to do anything about it, we call that business as usual. And if we do business as usual, this is where we're going, way up there. And in fact, the last time the Earth was that warm, and where we're at is 4.5 degrees C above pre-industrial, plus or minus about 1 degree C. The last time the Earth was that warm was 15 million years ago. 15 million years ago. Yeah, that's 12 million years before our hominid ancestors came down the trees and started walking upright. That's a long time ago. But we're going to get there in 80 years if we do business as usual. So that's pretty serious. So what are the implications of that? What are the global consequences of that? Well, I've got a little video here I want to show done by the BBC. It's just a short clip, and they did a real nice job of talking about the consequences in 2019. So let's take a quick listen to this.
What do we know about the impact of climate change on the world's weather this year? Let's start in the Arctic. Summer 2019 has seen Arctic ice 30% below normal. This region is heating up about twice the average of the rest of the world and is causing what scientists call a positive feedback loop. That's where sea ice thins and melts, opening up vast expanses of dark ocean that absorbs more heat from the sun, causing further warming. This dramatic warming of the Arctic may affect the strength and position of the jet stream, which brings the weather to the likes of North America and Europe. Globally, July 2019 was the hottest month ever recorded, and the Northern Hemisphere had the hottest summer on record. France and the UK were just two of the many European countries to see their temperature record broken. Studies showed the heat wave in France was made at least 5 times more likely by climate change. July was also Alaska's hottest month in recorded history. Wildfires there and elsewhere in the Arctic Circle are estimated to have released 50 megatons of CO2 in just 1 month, the equivalent of Sweden's annual carbon output. Wildfires hit the UK too, but in February, temperatures reached over 20 Celsius for the first time ever in winter. And on the other side of the world, Australia saw its hottest January on record, prompting health warnings and total fire bans. But by the laws of physics, a warmer world could hold more water vapour and potentially lead to more severe rainfall events. While the link between climate change and the Indian monsoon is uncertain, Mumbai has seen record summer monsoon rainfall totals. Iran suffered devastating floods in the spring of this year, as exceptional rainfall followed a prolonged period of drought. In Africa, Cyclone Idai was described by the UN as one of the worst natural disasters ever to hit the southern hemisphere. Heavy rain and coastal flooding led to the deaths of more than 700 people. Storms like these are expected to become stronger in a warming world. And in September, Hurricane Dorian became the second most powerful Atlantic hurricane in recorded history. Gusts of 220 miles per hour were measured in the Bahamas. An estimated 35 inches of rain fell, together with a huge storm surge. Sea level rise is already threatening other island communities, such as the Maldives. The Paris Agreement aims to pursue efforts to limit the global temperature rise to 1.5 degrees Celsius. But even under that scenario, sea level could rise by up to 77 centimetres by the end of this century. So 2019 has seen many examples of extreme weather that scientists predict could become the new norm in a warming world.
That's a nice summary of what happened in 2019. I want to now drill down a little bit more and into what consequences these are sort of. And I like to divide the consequences into two categories: natural consequences on the natural world, and human consequences. And so what we're seeing, of course, is increasing temperature of the land, ocean, and lower troposphere. The troposphere is the lowest layer of the atmosphere. It's surface up to about 40,000 feet where airliners fly. And it turns out what's happening is global warming is warming the lower troposphere, about half the altitude you're at when you're climbing out to cruise altitude on an airplane. But above that, it's actually cooling. So you're warming the atmosphere from below, cooling from above. That makes the atmosphere more unstable, and that's what yields these more likelihood of increasing frequency and intensity of severe storms. Increasing heat waves, and these things with humidity, the absolute humidity, that's how much moisture in the area, is definitely going up. But it turns out the relative humidity is actually going down because the temperature of the air is going up and the air can hold more water. So what this causes is, in areas of naturally wet areas, you have increased tendency for heavy rainfall and flooding, but in naturally dry areas where it's hard to get to 100% humidity and form rainfall, you're actually decreasing the likelihood of precipitation and causing greater drought. So it amplifies the differences. Wet areas get wetter, dry areas get drier, which is not a good thing. Decreasing snowfall relative to rainfall as the world warms, that's not good for us because that means decreasing snowpack in the Sierras, and we get a lot of our, I think about 1/3 of California's drinking water comes from the Sierras, so that's a big problem. Increasing frequency of droughts and wildfires, we're going to talk about that in more detail in a second here. Rising sea levels, big problems in the ocean with regard to ocean acidification and warming ocean, particularly impacting coral reefs. And decreasing productivity of fisheries because of decreasing oxygen levels and increasing acidification. So not a pretty picture. And it's also not a pretty picture in terms of human consequences. Increasing economic cost, increasing frequency of damaging weather events, increasing prevalence of wildfires and so forth. Increasing competition among nations for water and food caused by these problems. Increasing displacements of people and unrest in populations that are vulnerable to recruitment by violence extremist groups. A good thing to keep in mind is, rough numbers, is a 1 meter rise in sea level, which is about what we're looking at between now and the end of the century, will displace about 100 million people globally. And a 2 meter rise, which is within the realm of possibility, displaces about 200 million people globally. 30 million people in Bangladesh alone would be displaced by a 1 meter rise in sea level, and they have no place to go. India's not going to take them. Myanmar's not going to take them. They're already one of the most densely populated countries in the world. So you're talking about humanitarian crises and instability in parts of the world that are already very unstable. So big problems there. So, now we're going to talk about local consequences and really drilling down to the effect of climate change on California and even Monterey County. And what I'm going to be presenting is taken from the fourth assessment report, which was funded by the state of California. About every 2 years, the state of California funds these research projects. This is the fourth report, came out in 2018. It was done by Scripps Institution of Oceanography. It was basically a modeling study. I want to talk a little bit about this slide, which I think is really important. And it does kind of motivate the value of models and trying to predict what's going to happen. And what this shows is fundamental differences between weather, climate variability, and climate change. And what differentiates those three classes of phenomena are increasing time scale and space scale. So what does that mean? Time scale is just a fancy way of saying lifetime of a phenomenon. Space scale is just a fancy way of saying the size of the phenomenon. And in that context, weather happens on space scales of 10 kilometers to about 1,000 kilometers, minutes to months. Climate variability occurs on timescales of months to decades, and climate change decades to centuries to millennia on out, and so forth. This is weather here: thunderstorms, tropical storms, etc., winter storms. Climate variability includes El Nino, which a lot of us know a lot about. We're familiar with El Nino. El Nino and La Nina. That is a very good example of climate variability, and it takes on the scale of roughly the scale of the Pacific Ocean basin, about 10,000 kilometers. Remember all those zigs and zags on that one chart I was showing? Well, that's what's going on here. That's climate variability. Climate variability. It's these things like the El Nino, the Pacific Decadal Oscillation. A lot of oscillations that occur on scales of months to a couple of decades, often involving interaction of the atmosphere and the ocean. That's not climate change. Climate change is happening on a longer time scale. Climate change, number one, is global, not local. It's not happening on the scale of just the Atlantic Ocean or the Pacific Ocean around it. It's a global phenomenon. But also, climate change happens on scales of many decades into the future. So, general rule of thumb, and this is a take-home, by the way, I want everyone to remember this. If you're looking at climate change, you need to be looking at a record that's 30 years or longer. If someone shows you a record that's 20 years or less, you are not looking at climate change. You're looking at climate variability. And you cannot draw any conclusions about global warming by looking at a record that's 20 years or less. Climate change deniers often do that. Look at this, Milwaukee is cool, the last 15 years it's going down. Well, what you need to say is, okay, show me the global record for the last 30 years. That's climate change. You're looking less than 30 years, you're looking at one location, that's climate variability, climate change. Now the other big difference here is climate initial, or weather prediction is an initial value problem. Climate is an externally forced problem. Now this is getting really geeky, but I can't resist, I'm going to have to go, so hang in there with me. And this is what weather prediction looks like. Weather is chaotic, and key aspects of weather prediction are described by chaos theory. In fact, the meteorologists invented chaos theory, studying the weather prediction problem. And accordingly, weather prediction is an initial value problem such that very small discrepancies in the initial state you start off in your forecast will grow over time. So the red curve here is the actual weather. The blue curve represent weather forecast, and you can see the error, which is the difference between the two, grows over time. And this limits the forecast time to about 7 to 14 days. Lots of times you'll hear climate change deniers say, well, you can't even predict whether it's going to rain 3 weeks from now. How are you going to tell me what the climate's like 100 years from now? Two completely different problems. This is the climate problem. And first of all, climate is not weather. Climate models are not weather models. Climate is the long-term 30-year average of weather. And this long-term averaging filters out the chaotic behavior of weather and transforms climate prediction into an externally forced problem, which is somewhat sensitive, relatively insensitive to the initial state. What really drives the climate are external forcing factors. The external forcing really drives the climate. And if accurate assumptions can be made about the external forcing, then you can get accurate predictions from your climate models. And by the way, one more slide here to illustrate this difference. This is sort of an analogy to weather and climate prediction. You're bringing water to a boil on the stove here. Weather prediction is the analogy of weather prediction is trying to predict the location of every bubble at every point in time. That would be virtually impossible. Climate prediction is trying to predict the average temperature of the water over time and how it impacts how vigorous the water is boiling. That's pretty easy. You couldn't do the bubble problem with a supercomputer, but you can do the how quickly is the average water heating up with a calculator. So the bubble problem is equivalent to weather prediction. The average temperature in the bowl here is equivalent to climate prediction. And you can do much better in terms of climate prediction than you can weather prediction. as long as you know the external forcing factors. And on timescales of centuries to a few thousand years, which is what we're concerned about with global warming, there are three and only three external forcing factors, and they are shown here. The first is the incoming solar radiation. The sun's output does vary, and it will definitely have an impact on climate if it varies over a long period of time, and it has done that in the past. The reflection of the solar energy from aerosols in the atmosphere, mainly volcanic ash, because when volcanoes erupt, they put ash up into the stratosphere, it stays there for a long time. That reflects the solar radiation away, it exerts a cooling effect on the climate. And finally, the greenhouse gases, and in particular the greenhouse gases that we humans are putting in. So in this study, the assumptions are made about solar radiation staying relatively constant, aerosols staying relatively constant, which means we don't expect any major changes in volcanic eruptions. And the assumptions are made on how the greenhouse gases vary. And there are various assumptions that are made, various scenarios. The scenario we're going to talk about is, in fact, the business as usual scenario. Worst case scenario, which says everybody gives up, follows the lead of the United States, withdraws from the Paris Accord, and just basically drill, baby, drill. That's the worst case scenario. It's called business as usual. And that's what we're going to be looking at here. First of all, just a quick schematic about what a climate model is like. A climate model is just a big computer model, or a big computer program, which solves the basic equations of physics, chemistry, and biology on a grid that's laid out around the globe, takes in the entire Earth, includes the ocean, the ice, the land, the atmosphere. So what's the best climate model? Well, there is no one best climate model. Although all the models are based on the same fundamental equations of physics and chemistry and biology, there was leeway in how those equations are implemented on this grid, in a computer model. And so you'll find that there are different models that do better in certain areas, and other models do better in other areas. There's no one single model, and it's the best. And so the way that's handled is the Intergovernmental Panel on Climate Change, the IPCC, which is sort of the international single authoritative voice on this matter, has a group of 30 to 40 climate models that have been accredited, gone through various studies and published papers and so forth, that they regard as being valid models. And they issue their forecasts and their prognoses and so forth based on a collection of these various models. Now, in the study we're going to be talking about, they forced them with two different scenarios. I'm only going to show results from the business as usual scenario. That's the most extreme case, worst case scenario. And some geeky stuff here. There's a way to get a more detailed picture out of these models using statistical techniques. Don't worry about that. And also there was a surface land model comes into play to help predict the effect of things like water runoff and so forth. Also, the sea level predictions I'm going to show you, and also some relatively new physics, which makes us think that the ice sheets are probably going to melt a lot faster than we think they're going to melt. So just with that background, we'll take a quick look here. And the first thing that comes out of the study is, in terms of California, is increasing prevalence of drought. In fact, from these runs, they basically did an ensemble run of 32 different models from the current time out to the end of this century. And what you see there is severe droughts become about twice, severe and extreme droughts. Severe drought would define to be one that happens about once every 20 years. Well, it's going to start happening almost every 10 years. Extreme drought would be one that happens every 50 years, happens about every 25 years. So increasing prevalence of drought. Not a good thing for California, not a good thing for us here locally either. Now here's a bit of a paradox I'm going to show you. It's going to be a little bit puzzling. And that is, now I'm showing you the percent change in annually average precipitation at the end of the century, the last 30 years of the century, averaged between 2070 and 2100, compared to 76 to 2005. And this is the 2070 to 2100 results. And what you see here, except for parts of Southern California, the precipitation is actually going up. So how can that be? How can I tell you we're having greater, more frequent droughts, but yet the annually average precipitation is actually going up? Well, that's because the dry years get drier, the wet years get wetter. And during the wet years, we're going to get a lot more precipitation than we typically get in a wet year. It also means increased storm activity, greater problems with high winds and all the storm activities that have affected us occasionally. And you can kind of see that right here. Precipitation is pretty significant along the Central Coast. That reflects the fact of these stronger winter storms coming off the ocean and pummeling us during that period. So even though droughts are more prevalent, rain is actually going to increase. Now you might think, well, that's great. Oh boy, what we really need is Cynthia Garfield knows very well. we need water here. So this is really good news. Well, it's not that simple, because I'm going to turn right around and tell you that, in fact, there's another part of the puzzle here, and that's the temperatures getting much warmer. Now, fortunately, along the coast here, we're not as impacted as inland areas. You can see there's this gradation as you go inland, it gets warmer and warmer. But certainly on the coast here, we're going to be warming about 4 degrees centigrade between now and the end of this century. And the thing about it is, in addition to impacting all aspects of outdoor activities and work and farm fields and so forth, increasing temperatures have a significant impact on the soil moisture budget. So soil moisture is how much moisture there is right here in the upper part of the soil. You can kind of think of soil moisture as being like your checking account, and there's inputs to it. You've got your incoming money every month that's going in your checking account, that's good. Then your groundwater recharge, that's money that's going into the savings account, that's also good. But you're also spending money. You're spending money with runoff, and that's not so good, particularly since the fact these wet years we're going to have heavy rain events, and a lot of that moisture is not going to get captured unless you've got a dam to capture it. It's going to get run off to the ocean. But also the big problem is the evaporation and transpiration. Transpiration, by the way, is just evaporation through the pores of plants. We all know what evaporation is. That's a very strong function of temperature. And as the Monterey County warms, evaporation and transpiration, in fact, the entire state, is going to increase and outpace the increased rainfall, such that even though the rainfall is increasing, because evaporation and transpiration is increasing faster, we're actually going to be drying out. In fact, the state as a whole is going to be drying out. What we're looking at here is percentage change in soil moisture. And again, soil moisture is like a checking account. It accumulates all these inputs and outputs. What we see is, particularly in Southern California, which we've got a real problem, that's where it's really dry, but even here in Monterey County, we're looking at a drying effect. The state in general is drying. This is going to put increased pressure on our water supplies. It's going to put increased pressure on the possibility of wildfires, being impacted by smoke from distant wildfires. I did a quick calculation to turn this into acre feet. Most people think in terms of acre feet in water. This amounts to a loss of about 60,000 acre feet of water between now and the end of this century. And for reference, the Monterey Peninsula uses about 10,000 acre feet of water per year. So about 6 times the annual use of water on the Monterey Peninsula we would lose in Monterey County between now and the end of this century. Drying out is a big problem here, so we'll recap here in a second. But now I want to move on to sea level rise. Being a coastal community, we're impacted by sea level rise. And on the right-hand side, here's a list of things that impact sea level rise here in California on the long term, which means months to centuries. First of all, it's thermal expansion of the oceans. The oceans are getting warmer, we saw that on that animation. And as they warm, they expand, and that causes the sea level to rise. And in fact, thermal expansion of the ocean has been the primary source of sea level rise over the last century, and it will continue to be the primary source. But also melting of the mountain glaciers, that water ultimately flows into the ocean, that causes the sea level to rise. Melting of the ice sheets. So far, it's been mainly the Greenland ice sheet, but the real concern is the West Antarctic ice sheet. That has the single largest accumulation of fresh water in the world, and that ice sheet is starting to melt faster and faster. A lot of concern about that. Turns out extraction of groundwater is actually very small, but it does contribute in a non-negligible way. And finally, there can be local effects such as El Nino. When you hear about an El Nino effect, it actually causes our sea level to rise by about 5 or 10 centimeters. So these are long-term effects. But in terms of what's the sea level today, on top of these long-term effects, we also have these short-term effects. Tides, and the tides vary, of course. You've probably heard about king tides, which are the highest tides. Weather, when we have strong winds, we get storm surge. Atmospheric pressure, if the atmospheric pressure is low, the sea level rises. It's called the inverse barometer effect. And even rainfall, heavy rainfall will actually raise the sea level locally. And of course surf. Large surf, even if the storm is far away, will cause the sea level to rise. So, the big concern is the ice sheets, in particular the West Antarctic ice sheet. It turns out there's enough fresh water in the West Antarctic ice sheet. If you melt it at all, and no one's saying that's going to happen, but if you melted it all, it would raise global sea levels by 57 meters, which means we would be underwater right now. So there's an awful lot of ice there. And the thing about it is we have not really understood how these ice sheets behave very well. We still don't, but people are starting to understand them more. And what we're seeing is they're melting faster than previously anticipated. And in general, the predictions of sea level rise have been very conservative. For example, if you go back and get predictions that the IPCC was putting out, 5 or 10 years ago, and then compare that to how the sea level has varied, you'll find that the actual sea level rise has been along the upper bound of their predictions. They've been very conservative. Sea level has been rising faster than previously predicted. And a big part of this is trying to understand what's happening here. And that is the warm water coming in and melting the ice right where it's attached to the land. The ice flows like this. And as it melts here, the ice sheets are starting to flow faster. And as a result, that produces increased calving of icebergs, which contribute to sea level rise. And so there's a lot of uncertainty here, but generally speaking, the trend has been towards thinking that it's going to be worse than you might imagine. So I'm going to show you results here. Now, I had to swallow hard about how I was going to do this, because what I'm going to show you is I'm going to show you the worst possible scenario. The worst possible scenario is this number right here. This is a time series. This is actually for La Jolla, California. This is from that fourth assessment report. They showed a range of results. This is the most likely, a little less than 2 meters. This is the worst case scenario. We're going to look at the worst case scenario. The results of La Jolla would be very comparable to what we would have here, so that's valid. This is the worst possible case. This says we've got the tides, the highest tide, the worst storm, everything's happening all at once, plus the worst possible outcome for the ice sheets. It's thought to be the most worst physically thing that could happen. So why am I showing you the worst case scenario? Well, partly because you kind of want to see how bad the worst case could be. So if you're a long-term planner, you kind of want to know what's the upper bound and how bad things can be. But also, there's nothing magic about the year 2100, because the sea level is going to continue to rise after 2100. If you're willing to wait long enough, it's going to get here. Because here's the thing. Here's something a lot of people don't know about sea level. And that is, there is a long, long, long time lag between warming Earth and rising sea level. When I say long, I mean many centuries. So for example, let's assume we are able to achieve the most stringent goal of the Paris Accord and hold global temperatures to 1.5 degrees centigrade warming, which I think is unlikely. But if we were able to do that, you might think, wow, great, we're good, we can handle this. The problem is the sea level will continue to rise for probably 500 to 1,000 years until finally the ice sheets come into equilibrium with that warmer temperature. It takes many centuries for that to happen. And by the time that happens, the sea level will have risen even above here. Now that may be 500 to 1,000 years from now, but we still need to think about that, think about the fate of future generations. How do we know that? Because we go back and look at the historical geological record. We can map out how warm the Earth was back millions of years ago, and we can also map out where the sea level was, where it ultimately got to. And we find that if the Earth was just 1.5 degrees above where we are now, which is where we may go with the Paris Accord, the sea level ultimately ended up about 10 to 13 meters above where we are now. So that's part of the motivation for showing this worst case scenario. So there are 3 areas of concern if we have this 5-meter sea level rise: Castroville, Moss Landing, Watsonville, parts of Monterey, parts of Carmel. So we'll zoom in here. This is what a 5-meter sea level rise would do to Carmel. There's some neighborhoods here that would flood, and some of these neighborhoods actually flooded before when the Carmel River has flooded, I think, down along here. So that's what that would look like. And this is what it would look like in Monterey. Substantial parts of Cannery Row would be flooded, and substantial flooding along the wharf here. Del Monte Avenue would be flooded in substantial areas.
Is that worst case scenario, Mike?
Yes, physically can't get worse than this by the year 2100. If you're willing to talk about the year 2300 or 2400, it could be worse than this, because the sea level is going to continue to rise. Unless we're able to bring the Earth's temperature down, unless future generations are able to bring the temperature of the Earth back down to pre-industrial levels. Here's what it looks like in Castroville, Watsonville, Moss Landing, substantial flooding. So just to summarize now, what would happen under business as usual scenario? Increasing likelihood of severe and extreme droughts, with droughts happening about twice as often in terms of their severity. Increasing temperatures, with the temperature in Monterey County rising about 4 degrees centigrade, about 7 degrees Fahrenheit. That's the average temperature. Increasing rainfall, more frequent and severe storms in the winter, with increasing risk of damage to property from wind. Increasing extreme precipitation values, presenting challenges for storm drainage and flood control. Decreasing rainfall in the spring and fall, resulting in drier conditions heading into summer seasons and fall fire seasons, which is really a bad thing. Slightly increasing rainfall overall, but an overall drying out of the soil and vegetation as a result of increasing evaporation and transpiration due to increasing temperatures outpacing the effect of increasing rainfall, increasing prevalence of local wildfires and smoke from distant wildfires. Less precipitation falling as snow, more as rain. That's not good for the Sierra snowpack. And of course, it has decreasing supplies of fresh water with negative impact on population growth, agriculture, and a wide range of human activities. Rising sea levels, particularly after 2050. Things really tend to take off after 2050 based on this study. And threatening oceanfront properties, particularly after 2050. And in the most worst case scenario we showed, there would be substantial flooding in those three areas I mentioned. Okay, take a deep breath. You survived the science part. Now, I want to talk just briefly about legislation. And I want to talk particularly about the Energy Innovation and Carbon Dividend Act of 2019, the ICDA, sponsored by the Citizens Climate Lobby, which I belong to. And by the way, we have a very active Monterey chapter of the Citizens Climate Lobby. And the two co-chairs of the Citizens Climate Lobby are here, Muriel, stand up, and Linda. And if you want to get involved with CCL, please see them after my talk. They've got some material to help you sign up and get involved. But the big thing that CCL has done is sponsor this Energy Innovation and Carbon Dividend Act. And in fact, this act has sponsored other pieces of legislation that are going forward. And the idea here is it puts a fee on fossil fuels, which starts low and then grows, and that exerts pressure on people to reduce their fossil fuel usage. But it takes that money and gives it right back as a dividend, carbon dividend. And it's such that people who use a low amount of fossil fuels actually make money. People who use, or heavy users actually lose money. So that's a way to encourage less fossil fuel usage. There's also a border adjustment, also known as a tariff. And it will reduce CO2 usage by significantly over the years. And that legislation, which is shown right here, inspired at least 3 bills in the House, and there are companion bills on the Senate side. And in particular, I want to point out the Climate Action Rebate Act, which is sponsored by our own guy, Jimmy Panetta. And I particularly want to put in a good word for Congressman Panetta. The way I like to think about it is there are 435 members of Congress, and only 4 have sponsored bills like this, and he's one of them. He's in the upper 1%. And his bill, definitely inspired by the CCL bill, but in many ways more aggressive. Ultimately, these bills will collapse down to 1 and go forward. That's not going to happen until there's a new Senate and a new president, but at some point, there's a good start. At some point, we expect this will come into play and will be an important part of the solution. A couple of really fascinating and powerful things happen related to this, and that is Yale economics professor William Nordhaus, who's kind of the godfather behind this carbon fee and dividend concept, won the 2018 Nobel Prize in economics. Also, in January of 2019, in the Wall Street Journal, 27 former Nobel Prize winners in economic sciences, 12 former chairpersons of the President's Council of Economic Advisors, 4 former Federal Reserve chairpersons, and 2 former Treasury secretaries endorsed carbon fee and dividend. That's a lot of horsepower behind this concept. Very significant. And finally, Canada actually adopted their own version of carbon fee and dividend. Linda Charles, Maribel Andonian, they know a lot more about this than I do, and this is really a good news story here. You probably heard about the Green New Deal. The Green New Deal is not a piece of legislation, it's a House resolution. It's sort of like a general outline of where we want to go. And it's not all about climate. There's a lot of other social program kind of things there, but it does talk about achieving net zero greenhouse gas emissions, building smarter power grids, upgrading existing buildings, and removing pollution and greenhouse emissions from transportation and agriculture sectors. I want to move on finally to mitigation. I strongly recommend this book, Drawdown. Project Drawdown is a nonprofit founded by noted environmentalist Paul Hawken. This book was a national bestseller. You can go on their website, just Google Drawdown, get everything that was in the book, and it's really impressive. They identify 80 solutions for solving the climate problem, organized into 7 sectors. These solutions are combinations of technology and behavior and strategy. Here are the 7 categories, and they do a great job of quantifying how much greenhouse gas they'll remove over a 30-year period. Food is number 1, may surprise you, but food production has a very large carbon footprint. Food is number 1. Electricity generation is actually number 2. You might be surprised that transportation is actually at the bottom of the list. It turns out the transportation is not that large in terms of the global emissions. Just give you a feel for it, I'm going to show you the top 10 here. You'll recognize some of these things. For example, offshore wind turbines, solar farms, rooftop solar, but some that may not be so familiar. What's educating girls got to do with this problem? Well, Educating girls in developing countries keeps birth rates down, and that's a big part of the solution. What the heck is refrigerant management, which is actually the number one thing? Well, it turns out those F gases, those fluorinated gases, one of the class of those gases is called CFCs, coolants in refrigerators and air conditioners, and they are very, very powerful greenhouse gases, and they have very long residency time in the atmosphere. And the concern is people taking air conditioners and refrigerators and throwing them on the landfill. And ultimately they rust, and those greenhouse gases get into the atmosphere. There's a process you have to go through to recycle a refrigerator or an air conditioner. And in lots of parts of the world, they're not willing to do that and spend that cost. But if you don't do that, then we're putting very powerful greenhouse gases into the atmosphere. So there's a cost associated with this. First of all, what will be achieved by this? Over 30 years, if all the recommendations, the 80 solutions of drawdown were implemented, over a 30-year period, it would remove about 1 trillion tons of CO2, which is in the ballpark of what the Paris Accord is asking for to achieve the 1.5 degrees C limitation. So that would be great. So what would that cost? So what would it cost to achieve the Paris goal? The answer is about $30 trillion spread out over 30 years, which is about 1.25% of global GDP, about 1.25% of global GDP spread over 30 years. The kicker here is it would result in savings of about 74 trillion. So you spend 30 trillion to save 74 trillion and save the world, by the way. So that's a good deal. In terms of how it would impact the U.S., assuming every nation pays 1.25% of their GDP, and then that would, in the U.S., would amount to about $250 billion per year, which is a little more than 1/3 of the defense budget. So that's a lot, but doesn't mean it's not doable. It's kind of in the ballpark of things that potentially could be achieved. Okay, finally, I want to make some closing comments here, and I'm actually going to call on Sir David Attenborough, greatest naturalist of our time, to make closing comments for me.
Standing here in the English countryside, it may not seem obvious, but we're facing a man-made disaster on a global scale. In the 20 years since I first started talking about the impact of climate change on our world, conditions have changed far faster than I ever imagined.
Before we started to burn coal, the amount of carbon dioxide in the atmosphere was about 280 parts per million. It's now over 400 parts per million. And the planet gets warmer and warmer.
We are seeing the impacts of climate change now play out in real time. They're no longer subtle.
We're not just talking about inconvenience, we're talking about people's lives, their livelihoods, and their communities being damaged.
Join the dots. It's happening. It's happening in your world. It's happening in my world. And let's be very clear about this. It is going to get much worse.
It may sound frightening, but the scientific evidence is that if we have not taken dramatic action within the next decade, we could face irreversible damage to the natural world and the collapse of our societies.
There are thousands of scientists around the world in almost every single country working to understand what will happen in the future if we don't act, we don't do more. They predict that if we carry on as we are now, where CO2 continues to increase, we would hit 1.5 degrees global warming by between 2040 and 2050.
We're on course to go through 1.5 degrees in just a few decades' time. Models differ slightly as to exactly when. And not long after that, we're on a trajectory to go through 2 degrees.
It really becomes difficult to see at such levels of warming how we're going to maintain our agriculture such that the population of the world can actually feed itself.
Ensuring people have access to clean, safe drinking water will become much more difficult.
Developing countries that are at the front line of this battle.
Those parts of the globe which will suffer the most and the soonest are not those parts of the globe which have actually loaded all those carbon dioxides in the atmosphere in the first instance.
But you have to understand this is also a crisis for the world. The fact is that if the poor are suffering today, then the rich will also suffer tomorrow.
We're running out of time, but there is still hope.
It's actually not that complicated. We need to shift our energy system away from fossil fuels that produce greenhouse gases and towards renewable energies that don't.
We still have time to turn everything around, to pull the emergency brake and to take action. But that short period of time isn't going to last for long.
There's a message for all of us in the voices of these young people. It is, after all, their generation who will inherit this dangerous legacy. We now stand at a unique point in our planet's history, one where we must all share responsibility both for our present well-being and for the future of life on Earth.
Thank you. You've been a great audience. Questions?
We have time for some questions. I know some of you may have to go.
Thank you. Mike, I know you're familiar with our third largest employer in Monterey County, that's the military. And can you speak to the military's approach to climate challenges?
Yes, the military actually has been quite ahead of the game on this. In fact, one of my former Navy colleagues, Admiral Dave Titley, who was here some years ago, graduate of the Naval Postgraduate School, formed something in the Navy called Task Force Climate Change to position the Navy to deal with climate change. The issues that climate change affect the military kind of fall into three categories. One, different missions, new missions. For example, ice-free Arctic. As the Arctic becomes ice-free, more commerce goes up there, and we have to be able to protect that commerce and deal with that. The second is the impact on military bases. Rising sea levels are causing a big problem for the naval base at Norfolk, the world's largest naval base. But there are other facilities around the world that are being impacted, military facilities around the world that are being impacted by climate change. And the third one, perhaps most concern is, and we kind of touched on it briefly here, was climate change is an accelerant to instability. It causes more likelihood of conflict in unstable areas. And we've seen that in Afghanistan, we've seen that in Syria, we've seen that in other places. So the military is very concerned with climate change, and the military has been very much ahead of the game in dealing with climate change.
To bring this home, the Salinas Valley Basin Groundwater Sustainability Agency has prepared a plan forecasting groundwater sustainability into the future, and the assumption in that plan is increased precipitation, and it doesn't take into account runoff or transpiration or evaporation. So this was extremely informative to me.
They need to hear my talk.
You're right.
I am concerned with the approaches that we do take to climate change now, and I feel that they are too little, too late. My question is there any more radical solutions to the problem that we have today?
Well, the drawdown stuff is actually pretty radical. If we were to implement all the recommendations of Project Drawdown, we would be on a good path. And like I said, there's a big bill. There's the $30 trillion investment up front required on that. But I appreciate your comments about the multinational corporations. And and by the way, I'm going to be teaching an OLLI course at the end of January, focusing on climate denial community. And there is a very active climate denial community out there, funded to the tune of about $1 billion a year, mainly by the fossil fuel industry and various foundations such as the Koch Foundation that have large investments in fossil fuels. And that $1 billion a year funds a lot of climate denial kind of stuff, which creates doubt among people. Doubt among people creates politicians who are not willing to take action. So there's a lot of truth in what you're saying there. I think we have the technologies, we have the plans, we have the strategies in place. It's a question of finding the political will to implement them. And right now, it just isn't there.
Is there any well-funded counter to those well-funded climate denial lobbies? Because they have much of the power, political power in Washington at the moment.
Well, there are groups like CCL. I wouldn't say it's well-funded, but it's a grassroots kind of thing. I think there are CCL chapters in just about every county in the whole country. And I encourage you to get involved. Talk to Mary Bellendoni or Linda Charles if you can catch them on the way out here, because it's a grassroots kind of thing. And that ultimately can win out.
What is
is your opinion on the very quietly developed by about 10 countries, small modular reactors for, say, desalinization as well as for local power?
Are you talking about nuclear power?
They don't call it nuclear power because there's a couple of other products they're using as well, but they're small modular reactors.
Are they nuclear reactors?
Some.
Okay.
Some are other products. It's a reactor, meaning it's inside contained in a module. You transport it to where you need the power. And a single module is producing enough power for a village or a town of 27,000. But it's excellent size for desalinization, which California could greatly use.
I'm not familiar with that technology. I'll definitely look into it, but I can tell you I'm not a big fan of nuclear power. Having said that, of the 80 solutions on Project Drawdown, number 20 is nuclear power, but they see it as an interim solution, not as a long-term solution. Long-term solution, I believe, is really going to green energy.
Would you put up the slide again on drawdown that showed food as the #1 way and address the food issue?
You can actually see it here. There's a couple of food issues. Plant-rich diet is like number 4 on the list, number 4 out of 80 solutions. It turns out there's a very large difference between carbon footprint of a plant-based diet compared to a more meat-based diet. Particularly beef production, beef and lamb production is very carbon intensive. And the problem is developing countries are increasingly shifting their diets more towards the Western diet, more like our diet. And so they're putting more into beef production and lamb production. And that's causing their carbon emissions to really increase. Another big issue is, we throw away a lot of food. It turns out the world throws away about 1/3 of the food produced. If we could just quit throwing away so much food, that can significantly reduce the amount of greenhouse gas emissions, because food production is very greenhouse gas intensive, no doubt about that. So moving towards a plant-based diet, throwing away less food, eating local is another significant thing. If you're going to eat lobster, you want to eat lobster caught in California, not lobster caught in Maine, because you're paying to fly that lobster all the way over from Maine. Not so good, with the greenhouse gas emissions of that airline flight. So some of the things we can do are shift more to a plant-based diet, which actually is healthier, and avoid non-local food as much as possible, and throw away less food.
Thank you for your talk. I know you're a climatologist, but there's another aspect of CO2 in the atmosphere, and that is the acidification of the ocean.
Absolutely.
Something like 60% of our oxygen comes from the oceans. Could this affect that source of oxygen?
Yes. In fact, one thing that's happening is the oxygen levels in the ocean are going down as the ocean acidification is going up. Basically, the CO2 you put in the atmosphere, about 30% of it goes into the land and sequestered in the soil. That's good. We want that. About 50% goes into the atmosphere and contributes to global warming. That's bad. We don't want that. And then the remaining 20% goes into the ocean, is absorbed into the ocean. And when CO2 goes in the ocean, it combines with the water molecules and forms H2CO3, which is carbonic acid. And that starts to make the ocean more acidic. Now, the ocean is actually still basic. It's on the basic side of neutral, but it's trending more towards the acidic side. And the problem with that is just minor changes in ocean acidity. It makes it very difficult for the larvae of shellfish to form their shells. And it's hard on corals. It's hard on all kinds of crustaceans and shellfish. For example, I learned recently that there's a oyster company up north of San Francisco up there, and they actually have to go to Japan to get their larvae, because the larvae along the California coast, they can't make their shells. It's too acidic. So they're having to take that step, and that's only been the last few years that's happened. So ocean acidification, they call it the evil twin of global warming. It's a big deal. But ocean warming is also a big deal. It turns out the thing that's hurting the coral reefs the most is actually the ocean warming. They call it ocean heat waves. Just a couple degrees of warmer water sweeping over a coral reef combined with the higher acidification can cause the reef to bleach. They call it coral bleaching. It's because the coral turns white. What's happening there is the zooanthellae that are part of the coral reef, they die, and the coral expels them, and it ends up looking white and it dies. Big problem. Thank you for that.
Michael Clancy, thank you very much.
Sure, thank you.